Good afternoon. See, the problem of coming to a conference for only a single day is that you end up having to do 3 talks in one day. But are you tired? That was very weird. Okay. Well, let's pretend we're not tired. We've got beers coming after this, right? And there's only one thing between me and you and the beers, and that's me. So I'll try and be very, very, very fast. Okay, so I'll say the same thing that I said before. This is, again, it says gentle, it says introduction to reactive extensions and reactive programming. If you've done this before, probably might want to go to a different session because it is quite introductory. I will try and cover as many things as possible to give you a brief overview of what reactive extensions are about and what reactive programming is somewhat about. There will be a lot of demos, so we'll see a lot of code today, and hopefully it'll all run. So anyway, let's get started. So what and what not? Basically, we're going to see what the purpose of reactive extensions is, what it solves, what you can do with it, and potentially what not you can do with it, or where it doesn't fit. And again, like before, if you came to my previous talk, let's ask the why. So let's try and focus a little bit around this, the why. So first of all, because there's a reactive manifesto, and you saw this in my keynote. And in fact, if you go to this reactive manifesto, there are a couple of points on it. And the manifesto highlights that applications nowadays should be responsive, should be resilient, elastic, and message-driven. So responsive, there is this belief that we need to make responsive applications because otherwise, if we don't, our customers leave and they go to the competitors. Fortunately, if you're the only competitor, that's not a problem. They stick around. But by and large, we are trying to make somewhat of applications that are responsive, that aren't lagging, that aren't hanging, etc. Resilient is the idea that an application can, stand towards failure, etc. Elastic is, again, that it scales. Now, I don't have these scaling needs. I do use RX for certain things, so I'm not sure how much of this manifesto is required to tick in order for you to take advantage of reactive extensions. And message-driven is, well, around the concept of decoupling, which has been around for many years, from languages to frameworks to design to all of it. Point being that while you can read the manifesto and it does sound fantastic and it does sound encouraging and it does sound inspirational, it doesn't necessarily mean that you have to abide by all of those needs in order for you to take advantage of reactive extensions. It also doesn't mean that you need reactive extensions if you're doing all of those things, but certainly it does add certain value that you might take advantage of. Now, we do accept that asynchronous programming is hard. If you're as old enough as me, you remember the days when you used to play like, solitaire winning streaks with windows hanging. And we kind of have that same problem, except now it's called a different version of Windows, or the spinning wheel of death of Apple, etc. And we know that basically it is kind of hard that we get hanging applications that are non-responsive. And applications somewhat require it, and whether it's a desktop application, which definitely, the last thing you want to do is have your application hang, whether it's a mobile application, whether it's web application, or server-side. By and large, what we want to try and avoid is applications to hang and to become unresponsive. So any of these that we're doing, more or less, all have the same need. Now, we've attempted to ease this. We tried with threading, and it worked well, and then we killed ourselves in a deadlock. We tried async await. C# introduced the language construct async await, and they said, this is a very, very easy way for you to introduce asynchronous programming into your project. And we thought, okay, this is fantastic. So all I have to do is decorate every method with async. Yes. So we did that, and then they said, well, that doesn't really work because you have to decorate every single method down the call chain with async as well. Otherwise, it really wouldn't make sense if I'm just asynchronously waiting on certain parts of it. So now if you look at applications in C# that are using async await, all you see is a lot of async await, a hell of a lot of noise. If you're doing Java, well, you've had similar things. You've had this concept of futures. And if you have been doing any Node.js application development or JavaScript development, you probably have learned of callbacks, which are the new hell, right? We went from DLL hell to callback hell. And sometimes callbacks are like called the tilted Christmas tree, because if you look at it, it's basically callback after callback after callback after callback after callback, because we're constantly using closures to be able to access whatever it is that we want to do. The idea being that, you know, if you're not familiar with the concept, it's just a function that takes another function, and when the computation is finished, it will invoke the function that you've passed in. The problem is that that function in turn might require another function, and therefore you get this kind of chain of callbacks. It's not pretty. JavaScript has introduced the concept of promises to try and circumvent this, so there is that attempt to do it as well. But the thing is that here what you see already a pattern in which, depending on the language, depending on the way that we do it, it kind of starts to vary. So we now have to know all of these different ways in which we want to try and attempt to ease this concept of synchronous programming. The other issue, of course, is that when we try to combine asynchronous operations, it starts to become harder. So if I've got an asynchronous callback, and then from that I'm waiting for the result in combination with another asynchronous callback, it's not always that easy to combine these things. And as I said, different languages use different techniques, which kind of makes it somewhat less convenient to work with. So that's where kind of reactive extensions comes in, and their idea there is to make an API for asynchronous programming with observable streams, which basically means, well, we'll see. And the big important thing there is choose your platform. And that really is choose your platform, because this is available in a variety of different languages. So in RX, everything is a stream, basically. Everything. Think about it as a stream. And it's observable. So that makes complete and utter sense to you, right? All I'm saying is that everything is a stream and it's observable. We'll see what that means, obviously. Right now, let's take a step back and look at that a little bit. So what is programming? Now, if you were in my keynote and if you were in the previous session, you would have known this. Programming is an art. We are craftspeople. By and large, you agree with that? Yes? No? No, we're not. In fact, you know why it's not an art? Today I read a Twitter tweet today in relation to Apple and Taylor Swift, and it said that don't make people do art for free. Therefore, I came to the logical conclusion that we are an art, because at the same time we do open source for free. So there you go. That's it. Anyway. Actually, all we do is just process data. I was joking about the craftsmen, craftswomen, all kind of that nonsense. All we're doing is just basically processing data. You saw this before, you know, I just take data in one form. I take water, I convert it into whiskey. I take data in one form, and I produce some output. Normally, in the old days, we used to do this sitting in little cubicles with these little walls that were separating us. This was our job, just processing data. We can call it fancy programming, crafts, arts, what have you. All we do is process data. Nowadays, in an effort to cut costs, they make us believe that open office layouts are much better. So they've even taken the cubicles away from us. But that's all we do. It's not glamorous, but hey, it's a job. So we're all basically data processors. And data, well, you know, we take data and we apply functions to it, and functions come in different forms. So we get dates of birth, we get, you know, sales, amounts, names, and collections, list of countries, collection of customers, etc. Just different forms of data that we're taking in and we're processing. And if you were in my previous talk, if you're not, let me just quickly show you how this is done. It's very easy. Right, so here is some data. Here's some data. So I can take just a list of elements, and I say list of numbers, 1, 2, 3, 4, 5, and I can loop through them and print them out, or I can use a higher order function which takes a lambda expression that says number, print out the number, or I can use this syntax because in Kotlin there's this convention of not having to use the brackets if the last parameter to a function is another function. Very simple. All I'm doing is just taking data and processing it. And then I can do things like flatten the data, so I have a list of albums and I can flatten that and pass in predicates to filter on it and then map that out to a different result. And I could do all of these bunch of things. And then, of course, I can combine that. So I can take a list of numbers, and then I can filter it. Those are divisible by 2, and then get the last number from it, etc. Point being that basically I'm taking data, and I'm using these functions, which are higher-order functions, to process that data. Very simple. And that's why one of the things that's important when we start to get into reactive programming is this concept of functional programming. We need to start to think of things as lists, as collections, as scalars, and start to process them using functions, because they kind of go hand in hand. Okay? So that's a very, very, very brief introduction to functional programming if you haven't seen functional, if you didn't come to the previous talk. Now, if you look at the code, what we're doing basically, we've got this concept of iterable, which you're all familiar with in Java as well, and then we have this iterator. And what we're doing is every time we're just calling the next function, and we're just getting data out. We're just saying next, next, next. And then we have normally this other function, which is called hasNext, which tells us whether there is data to come out or not. And what we're doing is iterating over this data. So if you looked at the previous example, all I'm doing in the for each is just basically iterating over those elements. But each time I do this, there's a blocking call, right? So of course, this is the main thread of an application. It's a console application that starts and finishes, so it's not a big deal. But if I were to do that in an Android app or in a desktop app, that would basically block the call. But again, that's not a big deal because this call is absolutely instantaneous. So it's never going to block. Now, replace that kind of call with something like this, whereby I filter by a specific profession. I then go to the database. Get growth figures is some function that goes to the database that gets the data based on a specific city. And then on that, I display the growth. So now I'm combining functions. And in that combining functions, I'm invoking functions that can potentially take a long time. Therefore, right now, my application thread could be blocking. And we shouldn't block, because when we block, bad things happen. Our customers go away. And if you think about it, all we're doing constantly in these types of calls is just wait for data. We can wait for data from a socket server, we can wait for data from a file server, from anything that you can think of. All we're doing is just waiting for data in order to be able to process this data, get it and process it and combine it with something else. So if that's all we're doing, why are we waiting for the data? Why instead of waiting for the data, why don't we just get notified when that data comes? Why instead of just have like a busy loop waiting for data, why don't we just go off and do our thing, and then when that data comes, just let us know. And that's basically what we've tried to do with callbacks. That's basically what we've tried to do with threads, is just create this auxiliary thing that allows us to go and do our thing, and then when it's ready, come back. Kind of like an on-data-ready event. I mean, we're all used to events that we've programmed with back in the UI days, etc. You know, on mouse click, on mouse move, etc. These are all basically events. So it's kind of like the observer pattern, where I observe, subscribe to something, and I observe it, and then when something comes in, I process that information. So in essence, if I were to take that iterator and that iterable, and instead of pulling data, if I could like kind of switch that to an approach of waiting for data, then I could come up with something like this, which I have, whereas before I had an observable, before I had an iterable, I have an observable, and before I had an iterator, I have an observer. So now I have this function, which is subscribe, that says, I'll just subscribe to data, and when data comes, I'll do something with it. And then I have an observer which says on next, which is when the next comes, the next element comes. Uncompleted, which would be somewhat the equivalent of hasNext, except that in this case it will notify me via an event. And I add an additional one which says on error, which is useful because it allows me to know if something's going wrong. And that's what we're doing. Basically, we're taking the iterable and we're mapping it to an observable, right? We're going from the pull model to the push model. And this is actually a concept called duality. And there's your definition. In mathematics, a duality, generally speaking, translates concepts, theorems, or mathematical structures into other concepts, theorems, or structures in a one-to-one fashion, often by means of an involution, which is a fancy word of saying that if I take a function and I apply the same function with a parameter, I get this parameter that I put in. If the dual of A is B, then the dual of B is A. There you go. Law of De Morgan is another example of applying duality. So the negation of A and B is equal not A or not B. And in fact, Eric Meyer, how many of you have heard of Eric Meyer? So Eric Meyer is the guy that came up with reactive extensions, and he came up with it when he was at Microsoft and on C#. And this is one of the examples of something that came out of Microsoft that's been ported over to other ecosystems. Recently also, well, a few years ago, Microsoft also made it open source. So now RX Java is kind of like the home for all of the different languages. And Eric Meyer came up with this reactive extensions. And that's why he left Microsoft. His company now is called Applied Duality, which is, now you see why, because all he was doing is applying duality to the concept of iterables and iterators, which in C# is INumerable and INumerator. In C# we prefix our things, interfaces with an I. In Java, you suffix them with an implem. So reactive extensions, in essence, is just an extension of an observer pattern. And it's got a bunch of operators to work with sequences of data and their composition. And that's the key thing. That's why I've underlined it, because the operators are one of the key aspects of reactive extensions. Whereas with functional programming, we kind of have all of these functions which are filter, map, reduce, fold, etc. RX brings its own versions of those functions. So it brings like a suitcase of tools allowing us to use observables to deal with streams of data using the observable, the reactive pattern. And one of the aspects that it does is it abstracts low-level threading. So all of the things that we saw before around promises, futures, async, await, threading, all of these things, that's basically, in essence, it's the same thing. It's just trying to raise the level of abstraction so that we can deal with data in a more expressive way and not have to worry about the threading aspects of it. Having said that, we can still run into problems, and we'll see later on. Okay? But, you know, this is no way, once I gave this talk and someone said, but how is this actually different to threading? It's not. How is it different to callback? It's not. It's trying to do the same thing, trying to do asynchronous programming, but in a way which is probably more expressive and easier to do, but once we kind of grasp the concept of what's happening. And it really is available for every single platform that you can think of. So there's the Java, which is RX Java. RX Java, by the way, was implemented by Netflix, by Ben Christensen. So they liked what they saw in C#, and they took it over, and then they translated it to Java, and then they released it under RX Java. And under that umbrella then came support for a bunch of other languages such as RX Clojure, RX Groovy, RX JRuby, all of these. The original one in .NET is still RX.NET. So from one side you have these languages which basically all they are is implementing this observable pattern and applying all of those extensions that we were talking about. And on the other side you have kind of libraries, frameworks, which allow us to leverage this API that RX Java provides, or RX provides. So now we have, for instance, RX Netty, which I'm sure you're familiar with Netty, and it allows you, it's a socket, TCP, UDP, all of these types of programs you can do with Netty. And what it allows you to do is create an abstraction over Netty to use the same kind of syntax API that you do with RX. So you have RX Netty, RX React, RX Android, RX UI, etc. These are just frameworks on top of it, libraries. Okay, so given that, now we're going to just switch to demos, and I'll show you a little bit how this works. Now let's start. Okay. This is a perfect time for me. I did this on purpose, so I said to IntelliJ, please hang so I can drink some water. Maybe I should switch to Eclipse. I'm joking. Right. Shh, did I say that out loud? Right. Okay. So what I want to start with is show you some code that you should never do in your life, which is a perfect way of starting introducing a concept that you've probably not seen. Bear with me. Basically, we talked about in Rx you have an observable and you have observers. So you have this thing that you can observe, that you can subscribe to, and then you can start to process when events come in. Now, in order to do that, you need to implement an observable. And this is an observable of string. If I did an observable of string takes a constructor parameter, which is something that is observable, but instead of me implementing all of this manually, I can use this helper class, which is onObservable, onSubscriber from iterable, which basically is a class that allows me to create subscribers from anything that's iterable. This is the full Monty. This is how you would create your own observable, but in essence, you will never do this, and we'll see why. And then from the other side, I have the observer. And in the observer, what I'm doing is I'm just saying, you know, on next, print out an element, on completed, print out a sequence completed, and on error, throw an error message. Now what the error does says, if there's an error, I will stop. I will just launch that on error event, and then I will stop. And if we run this, basically what you're going to see is element A, element B, element C, sequence completed. And for that to happen, what I've done is I've created an observable, passing in a list of iterables. I've created an observer, then the observable has subscribed to the observer. Okay? Very simple. Now again, this is my console application. So there's a single thread, it starts, it's going to do this, it's going to finish. So really here you're not going to notice much difference. You're going to say, why am I doing all this? Why don't I just do a list of, just like I did before? Because in essence, think that this would be in your normal application on a main thread, and therefore if you call something that takes up time, it will start to block. Let me show you an easier way to do that. So if I do an observable from, this is just a constructor which allows me to do exactly what I did before, but in a more concise way. So instead of having to now create that observable class, I can just say create an observable from an iterable. So here I can take an iterable, I can take a future even, I can take an array, any of those, and just pass it in, and now this is going to create an observable for me. So I've already cut down a whole bunch of code. Now I have the observable subscribe, and the observable subscribe can take 3 parameters. Well, it can take many. There's a bunch of overloads, but I'm putting the full 3 methods that would need to be passed. The onNext. What do I do when an observable is available to me? I call onNext. What do I do when an error message is thrown? I call print, line get error. What do I do when the sequence is completed? Like that. These are single parameters, so I don't have to be explicit. On the top one, I've been explicit. Now I do subscribe to that observable, print line something, and subscribe, print line something. Let's see what happens actually when we run this. So you see what's happening is that I'm subscribing to the observable, it's printing out A, B, C, then it's saying the sequence is completed. Then it's printing out something, and then it's printing out A, B, C. So the first thing that you'll probably notice there is that it's basically going in the order that I've defined in the program code. In essence, I'm just saying, you know, create this, do something, then print it out, then create it again. The other thing you should notice, and when we look at the threading and the blocking and etc., this will start to fall into place, but the other thing to notice is that every time I subscribe to an observable, it's as if a new thing has started. Okay? Let me show you another example. Observable refactor. This is similar as before. Again, it's exactly the same type of idea, but in this case, instead of passing a from, there's another constructor which allows us to pass in an object, in this case it's an anonymous object, in which I implement the call. So by and large, normally when you're working with Rx, you don't normally make your own observables. You only make your observables when you're trying to interact with something that doesn't have its own observable. The libraries that I mentioned, the operators, all of these pretty much provide you with a wealth of already good observables. But when you're trying to create your own observable, what you can also do is just create an anonymous object and then you call the method. So every time it would be called for this, call, and then I say T on next, T on next, T on next. This is the actual subscriber. So what this means is that on each time a subscriber comes in, I'm calling on next, on next, on next, and then I'm saying on completed. The observer, again, very similar as you saw before. I've got it on next, I've got it on completed, I've got it on error. And again, if I run this, we see I get element A, element B, element C, and then sequence completed. So these are all mostly just helper methods for us to be able to create observables. And since a lot of times we're trying to create observables from iterables, we have those helper methods like create an observable from, which is basically taking a future or an iterable. So now let's see something weird. Well, now, I'm going to comment out this line and I'm going to run this. Okay? What do you think is going to happen? Well, too fast. It told you what's going to happen. Nothing. Why is that? Why would nothing happen? The difference between this and the previous example is that I'm using this other thing here, another constructor called interval. An interval takes two parameters, a time interval, a time unit, which is, in this case, seconds, and the value. And what it does, it starts to spit out numbers on that sequence. So it says, start to print out 1, 2, 3, 4, every second. The problem is that by the time this starts, the program is finished. Let's see what happens if I do, for example, nanoseconds and run it. Oh, no, you don't want to do that. No, you don't want to do that. Now we want to do that. So, nothing. But, hey, if I run it again, sometimes something happens because it gave time. So the difference is that interval, as we'll see, actually doesn't run on the main thread. And here's what you now start to notice about how observables are not running on a single thread. Interval does something magical. It runs on another thread that we'll see later. That's why I have to put this while true and block my program in order for you to actually see the output, right? Now every second I start to emit an observable. Okay? So we've seen, how to create an observable using anonymous object, how to do the full thing, how to create it from an iterable, how to create an interval that just emits data for us. But one of the things that we said we want to try and do is try and combine these, right? Because the problem with asynchronous programming is that often we want to get data from different sources, and these can all be asynchronous calls, and then combine these. And that's where Reactive provides us with this wealth of ability to do this. So here, for instance, I'm creating two observables. One that goes from 1 to 10, and another one that goes from A to J, right? So A, B, C, D, etc. And what I'm saying is that I want to zip with. So I want numbers to be zipped with letters using this function. So every time an observable comes in from each of these, I will combine them, and I will say that, I'm going to create a new pair where Y corresponds with X, where X is from the numbers and Y is from the letters, and then I'm then going to chain this. So I'm going to chain it to call another function on it, that loops through them and prints them out. This line of code is exactly the same. The only difference is, whereas this one is acting on an instance of the first observable, this is just passing into observables. So it's a static method that's passing into observables. If we run this, you'll see that what it's doing is it says A corresponds with 1, B corresponds with 2, so on and so forth, right? Now, the power here is if you look at this, you're going to say, well, this is just functional pipelining, you know, what we saw before, where I just combine functions. The difference is that these are actually creating observables. So from is creating an observable. Zip with is creating an observable. So it's maintaining that asynchronicity. And that's, I said it right, asynchronicity. Okay? And that's done internally via, I mean, if you look at the zip with, okay, this does a zip, and then if we take a look at the zip, this just calls zip, and it uses this function called lift, which basically takes collections and then creates observables around them, okay? And that's the key thing to distinguish here. We're not simply just taking lists of data and then on those returning lists of data. We're taking observables and returning observables. And we're respecting the contracts that we have in observables, which is on next, on completed, and on error. And these are important. Okay. If we take a look at another example, which is blocking, here is a typical anti-pattern. Right? So if you remember this example with the interval, what I was doing is basically I was calling interval and then I was subscribing to it. But in order for us to see it, I had to actually put a busy loop so that we could see the output. Here what I can do is instead of put that busy loop, I can do a to blocking, which basically what it does is it blocks that observable. Now, why I say it's an anti-pattern is because normally you wouldn't use a to blocking, because if the whole purpose of us is to prevent locking main threads, to prevent locking the UI thread, to do this in a callback way so that we don't have to deal with all of this, why would we go and block an observable? Nonetheless, sometimes for certain reasons there is a need to block, such as doing demos, and you can actually use the to blocking, and what that would do is basically block the observable. Okay, in this case, it would never finish because it's always just blocking. So most of the things we've seen so far is how to do an on next, on next, on next, on next, and then an on completed. But we also saw that the observable has a third contract, or third method that it has to abide with, which is the on error. And the error handling is where it starts to become quite nice. So here I've created the full observable, and basically what I'm doing is I'm looping through a list of numbers, and I'm doing a random sleep. This is, you know, simulation, this is demo code. And then I'm calling on next for that number. I then check to see if it's divisible by 5. If it is, I don't ever throw an error here. You never throw an error, you never handle really the errors in the observable. What you do is you call on error. And in this case, I'm saying number exception. So I'm raising a number exception. This is just to make sure that it's unsubscribed, which we'll get to a little bit later. And then at the end, I'm saying T on completed. Okay? So let me just comment this out. And if we run this, what I'm doing is basically I'm receiving on the observable, okay, it works. Right, so I'm doing a received, receive, receive. It hits 5 and it says on error, non-implemented exception. Okay? Now, since I haven't actually implemented in the subscribe, I've only passed in a single method, right? I haven't passed in the other method names. So if I were to do, let me show you, if we were to take this away and then do something like subscribe, you can see here that I have the on next, on error, on complete. I've only implemented the on next. So I've actually not implemented the on error, and therefore the exception is basically passed down and it's raised as an exception in the main thread. Now, you can easily implement the on error and then do whatever you want with it. But one of the cool things that comes into play now is not just what you can do with the error, but what you can do if an error occurs. So here, let's uncomment this and come up and uncomment this out. Here what I'm saying is map, subscribe to the observable, and retry one time. So if an error occurs, retry again, right? So if we run this, you can see that it retries and then it ends. Now, if you run it again, it ends with a different value. But what's basically happening is that it's retrying. Now think of the simplicity there, and think of what you would have to actually do if you were to do that manually. Imagine instead of mapping a list of numbers, you were to make a call to an HTTP server and say, if it times out, retry 5 times. And if it works, great. If it doesn't, then just fail. With a simple call of retry and passing in the number, I've just added somewhat of error handling in case of failure. And I've said, you know, retry this 3 times or 1 time, etc. And of course, you can see that that takes other parameters. So I could also do retry, which in this case is retry with an exception. So here what I'm saying is retry as long as the exception is of type number exception, then ignore. I don't care. You can do that as many times as you want. So this will always print out 20. Right? Because the only error that is occurring in that observable is a number exception, and therefore it will ignore it. Right? So this gives us a lot of power in order to be able to now get those streams, process those streams in case there's an error, retry it, etc. And then once we have that, we can continue to do the processing. Now, in the example that we saw here of combining observables, right, what happens is that sometimes this and this can come from different sources. So, for instance, you could have, obviously this is both lists, so it's going to be instance, you know, I'm just going to loop through the lists. But imagine, for instance, you have one coming from a really slow server, and another one coming from a really fast database, and then another observable coming from user interaction or what have you, and you're trying to combine all of these. And then one of them kind of fails or goes slower than the other one. Now you've got an issue because, you know, one observable is emitting faster than the other one. So there is somewhat techniques to handle that, and there are operators to handle that. So here I have a list of observables, and then what I'm doing here is I'm saying buffer the 3. So basically this means just buffer, keep 3, and once you've got 3, then emit. Here, what I'm saying is debounce for 3 seconds. So if we run this, we can see what the result is. You can see that I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then here I have 10, 11, 12, etc. So what I'm doing here is using certain operators that Rx comes with in order to allow me to deal with somewhat what they would call back pressure, whereas we're getting sources much faster from one input than the other. And this is debounce, for instance, the typical example that they show you with debounce is because Rx is also available in the flavor of RxJS. So now you can actually use the same techniques when you're doing JavaScript on the client side. And one of the things they always show you as a stereotypical example is, you know, I'm in a field where I'm typing keys, and then once I've got something that matches, I'm going to send that to the server in order to offer a suggestion to the user. Basically what Google does. Now, if you do that every time there's an on-key press, you might not want to do that because there's too many requests going back to the server and not enough information. So sometimes also I could start to type something and then say, ooh, I've made a mistake, let me block it, let me delete it, and then start typing again. So the debounce is a very typical example of what you could do there. You could say, wait 3 seconds and then send me the information, right? In order for the person to think a little bit before they type. Now, none of these operators are going to magically solve this concept of back pressure. In essence, what that means is that, if I've got one source of information spitting up 10,000 times faster than the other one, at some point, things are going to blow. Right? We're going to get out of memory exceptions. Something's going to happen because this is not magic. Therefore, you're going to have to probably discard data or find some other way to deal with it. It's not going to magically solve back pressure for you. Let me show you a little bit more of an example where we have actually something working. So here I have a socket server, which is basically just reading. It's basically, I'm firing up a bunch of sockets that are reading data from a log file, which in this case is an HTTP server. So the sockets are running, and now I'm going to come to the reading from sockets. And here what I'm doing is basically creating an observable that reads from the socket. So every time it reads a line, it's going to say on next. Okay? And then what I'm doing here is I'm saying observe that observable and filter out a specific URL. In this case, twiki/bin rdiff main. And once you get that, in my case, I want to just subscribe to it and print it to the console. So if we run this, it will just sit there. And once in a while, when it comes across twiki bin rdiff, it will spit it out, right? So now you can start to see what cool things you can do with this, right? You've got a server log that you're monitoring for specific IP addresses or specific requests, and you want to get some information from that back. And when that comes back, you also want to get information from maybe the access log and map a specific error to a specific user at a specific time. And you can basically just combine these observables, make these calls, and then once you have that, do something with them. And all in a very clean and concise way. Pretty much everything that we've seen in the previous talk around functional programming, which is I'm just using functional pipelining to pipeline call after call. And behind the scenes, all of this is happening in a very asynchronous way that I don't really have to deal with. And how is that actually happening? So now let's go and look at some code to see what happens. So here I have the example that we saw initially, right? I have an observable from 1 to 10, and I'm saying subscribe. And I'm receiving it, and what I'm doing here is I'm using a thread name to tell you on what thread it's printing out so that we can see it. If I go to the function of that, all you can see is basically it's just getting the current thread and getting the name. And in my main app, all I'm doing is calling this version of the code. So let's run this. Now this is the observable from, okay? And you can see that why that makes sense and why that's been working all the time, because it's basically running it on the main thread. So it's getting a list of it's getting an observable over a list of iterables, and it's running it over a list of iterables, and it's running it over the main thread. Okay? Now let's go ahead and change this to the next call. And this one, what it's doing is it's using the interval, the example that I showed you before, and it's doing the exact same thing, printing the thread name. But then I'm also printing the thread name here. So this is the subscriber thread name, and this is the thread name of this function. Let's run this and see what happens. So you can see that the function is being called on the main thread, which is the result of this. But the interval is executing on a secondary thread, which is called Rx computation thread pool. And this is where Rx is abstracting away all of the threading for you. It is taking care of saying where I need to execute what. Okay? Now, what you can also do with Rx is shoot yourself in the foot. And we love to shoot ourselves in the foot, because you can change all of these parameters. You can say, you know what, I don't want you to subscribe on the Rx computational thread pool. I want you to subscribe on the IO thread pool. And you can do this in multiple ways. One of them is to just use the observed on chain call. And this takes as parameter scheduler. And if we go here and we delete this computation, you can see that I have computation, from, immediate, I/O, new thread, test, trampling, and all of these have different meanings and different contexts in which you would use them. So if we run this one, we can see that it's basically subscribing on the computation thread and just doing the same as before. Okay? So by default, it is on the computation thread in the interval. Now another way is here, I'm saying, notice the difference that here I'm saying what I'm observing on. Which thread am I observing on? But you can also define which thread you're subscribing on. So I'm changing the subscription thread here. And if we run this, we can see that I'm receiving on the thread computation pool. Okay? Now, most of the times when you create an observable, they actually say it's kind of like best practice to not force people to use this kind of approach of observe on, subscribe on, because it starts to become ugly and a little bit confusing. What you can do also is most observables have a third parameter, which is the scheduler. So when you're creating your own observables, you should kind of follow this practice of passing in a third parameter. So I can actually pass in my parameter here, and I can say create this observable using a specific scheduler. Okay? Now, since we're chaining observables, what's also important is the ability to unsubscribe, and we have to take this into account. Because let's say that I have an observable that's reading from a socket, and then onto that I make another call, which is basically lifting the result of that observable and creating another collection, another observable using lift, and then on that I'm doing some other call. Somewhere down the line here, I actually stop listening. We need to make that notify up the chain to all of those observables so that they make sure they also stop listening. In essence, a subscriber has unsubscribed, because otherwise things can just go on for years. I mean, if there's no one subscribed to a socket server observable, why am I even reading from it? Does it make sense for me to read from it? So that's why it's important when you're creating your own observables to make sure that you unsubscribe and you take into account unsubscriptions. If there is no more subscription, then you should basically stop doing what you're doing. And this takes us to the kind of last thing that I wanted to talk about, which is hot and cold observables. Okay? Now, everything that you've seen so far is pretty much a cold observable. And a cold observable means that something starts, I subscribe to it, it starts, and then if I subscribe to it again, it starts again. So from 1 to 10 is a cold observable. You know, anything that basically resets. So it's just, it starts on the subscription and it ends. The hot observable is something that's going on continuously. Something that whether or not I'm subscribed to is going to happen. So an example of a hot observable is the mouse. If the user is constantly moving the mouse, whether or not you're subscribed to it, what is the mouse emitting? Just a stream of data, which in this case is stream of coordinates. And that is a hot observable, meaning that this observable is acting over time. And if I subscribe at T1, I'm going to get some data, and if I subscribe at T7, I'm going to get some other data. But the data that came from T1 to T6, or T7, I've missed out on. I'm not going to get. The observable is going to continue whether or not we subscribe to it. Now, you can't really, I'm simulating creating a hot observable here just so that you see more or less what it happens. There are ways for you to convert a cold observable to a hot observable, etc. But so you see that here I'm doing first 0, 1, 2, 3, 4, and then the second one, as soon as it subscribes, it starts 5, 6, 7, 8, 9. So it's missed out on all of those initial values that were being emitted. And why did I say mouse? Mouse, because basically that's all it is. If you think of mouse, mouse is just a set of coordinates that's being emitted. And if we think what we were saying initially, which everything is a stream, there you go. Everything is a stream of data. A mouse is just a stream of coordinates. One last thing that I do want to show is when it comes to testing, because we're talking about time, Rx also provides great utilities for time. So here, for example, I have a test scheduler, and which also passing that third parameter to operators allows us to also pass in a test scheduler. So here I say observe, I have an observable interval that I take 5 and I subscribe to. And then I say test scheduler advanced by 2, advanced by 4. So basically it allows us in unit tests to perfectly simulate time over a period of time when we're working with that. Okay? So those are just kind of like an overview of all of the different things, all of the aspects, somewhat operators that you can get when you start to work with Rx. Obviously, when you get into more complex scenarios, you have to kind of deal with other aspects, but not covering those. Now, is this the silver bullet? And I hope you know the answer is no, right? Because there is no such thing as a silver bullet. Rx does help with asynchronous code and with combining results. And it provides us in a way of thinking about data as events, because at the end of the day, pretty much everything that we do deal with is just events. It's just some are static, some come over time, some are delayed, etc. And it also helps us quite a bit when we're trying to deal with error handling. Okay? But they're also, most importantly, it adds a layer of abstraction. So it takes away from the threading, it takes away from having the callback hell, and does provide us with the ability to now think of data not as collections, but as streams. And we can start to basically deal with these streams and act on them as the data comes through. But it does have some issues, because the learning curve isn't easy. And you also need to kind of come with the functional approach. You already have to kind of think in terms of, I have lists, I have collection of items, I have scalars, and I need to deal with those, and then on those apply all of the different aspects of the operators that Rx provides us. And of course, just like everything, you can still cause havoc if you start to mess around with schedulers and you subscribe on one scheduler and publish on another one. You can absolutely cause deadlocks. And it doesn't help with parallelism as such. This is about avoiding non-blocking calls in an asynchronous way, but somewhat concise and easier to read. If you want to learn more, I recommend you go to the ReactiveX website. There's a whole bunch of tutorials, and it's, you've got basically all languages, everything you can think of. And Andres Stalz has done a very good tutorial, the introduction of reactive programming you've been missing. And he's also created this other site, which is called RX Marbles. And RX Marbles is really great because it shows you all of the operators. And let me just show you this. RX Marbles. So RX Marbles. So here what you can do is you can select, for example, the operator, and then you can just drag it along, and it shows you basically what this is about. So for example, the debounce, if I take the 3 and drag it along, it shows us exactly what's happening. So it's very useful when you're trying to get familiar with these operators and learn them. Okay? So check out the RX Marbles site. Thank you. That's it.